Look at this. This is what the internet actually looks like if you tap into the wire. It's just noise, gibberish. Millions of times a second, your phone and your computer are sending this exact kind of noise out into the world. But what is it? And more importantly, why does it matter to you? Encryption, the system that keeps every password, every message, and every transaction private. Today we'll break down the two types that power it all, symmetric and asymmetric, and show you exactly how they work. To understand the noise, you have to understand the problem. The internet is essentially a crowded room. If Bob wants to send a private message to Alice, he has to send it across wires that he doesn't own. And that means Eve or anyone else sitting on that network can listen in. How do you talk privately when anyone can listen? The oldest answer is symmetric encryption. It's simple. Bob takes his readable message, his plaintext, and he scrambles it using a secret key. That turns it into ciphertext, the unreadable noise we saw earlier. When Alice receives the noise, she uses the exact same secret key to unlock it and read the message. So like one key, both to lock and to unlock the message. It's incredibly fast and highly efficient, but it has one fatal flaw. How do Alice and Bob agree on what the secret key is in the first place? If they send the key over the internet, someone can steal it. To share the key securely, you need a secure channel, but to have a secure channel, you need the key. It's a chicken and egg problem that stumped cryptographers for a long time. The solution is a mathematical trick called asymmetric encryption. Instead of one key, you generate two, a public key and a private key. Think of the public key like an open padlock attached to a mailbox. You can hand copies of this padlock to anyone in the world. Anyone can drop a message in the box and snap the lock shut. But once it's shut, the only thing in the universe that can open it is the private key, which you never share with anyone. But wait, if the padlock is public, how is that secure? Let's break that down. The algorithm that does the locking, RSA for example, is public. Anyone can read exactly how it works. That's not the secret. What makes it your lock is the combination you set. Alice and Charlie both use the same RSA algorithm, same lock type, but each person generates their own combination when they set up their key pair. Alice's public key is her combination, 7294. Anyone who wants to send Alice a secure message locks it with 7294. Charlie's public key is his combination, 5561. Lock with 5561, and only Charlie can open it. So when a third person, David, wants to send a message, he picks the combination based on who he's writing to. Writing to Alice, lock with 7294. Writing to Charlie, lock with 5561. Notice, the public key has nothing to do with David. It's not about the sender. It belongs to the receiver. If Eve intercepts both messages, she can see everything on the wire. Even if she has both public keys, it doesn't help her. The public key locks. It cannot unlock. Only Alice's private key opens Alice's messages, and only Charlie's opens Charlie's. Same lock, different combinations. Only the owner can open theirs. Now you can see why this matters. There is no personal arrangement between receiver and sender. No shared secret, no secure channel needed to get started. That's what asymmetric encryption solved. And that brings us back to where we started. Remember the noise from the beginning? All that seemingly random data traveling over the internet. It was never random. It was a message locked with a key that only the right person could open. That's encryption. And now you know how it works. Thanks for watching.